All right, so this is Intro to Computer Vision. We're going to learn how to build our own object detector and data sets. My name is Sage Elliott, and you can connect with me all these places. And I work at a company called plainsight. Find us at plainsight.ai. I think I shared some links in the chat earlier, but if you want to check out more about what we do, you can do so there. And also one other important link is if you want to stay connected, we have a Slack channel. It's a really good place to come and ask me questions after the workshop. If you're working on your own data set or trying to train your own model and you're having any issues, that's gonna be the best place to reach me at. Hit record. This is a reminder for me. I hit record, so we're good to go. Setup, again, we'll be using an online data science environment called Google Colab, so you don't have to install anything. We'll also be using an online data annotation tool. So again, that's the sign up link to get started in that tool. There's no card or anything required. You just put in your information, you'll get an email back, and you hit the link in the email and it'll take you to the tool. So what this workshop is, hopefully it's a super friendly introduction to computer vision. It's kind of designed for anyone with no previous experience, but knowing some Python will really be helpful when we get to the code. But if you've never programmed in Python or never programmed at all, don't worry, because you'll still be to run all the code and I will be talking about what's happening. Just don't get stressed out about it if it looks like a lot's going on. But you'll be able to come away, no matter your experience, with a really cool state-of-the-art object detection model, and you'll know all the steps of how to get there so you can create your own applications. So we're going to cover one, applications and basic intuition. It's going to talk through some use cases, and I'll want to hear from you about some cool use cases too. And then we're going to talk a little bit about intuition, like how deep learning plays a role into it. Then we're going to go hands-on and kind of see how to label your own data set in a whole bunch of different ways, and look at ways of how you can speed that up. So data annotation's a really long part of usually this process, and there's a lot of ways where you can help make it quicker. And then we're going to, again, like I said, jump into code and train a model. And then also I'll give you a link later that will give you a form to fill out, and you can get a certificate of completion, which I just redesigned yesterday, and I think it looks really cool. So just keep in mind, you can't learn everything in 2 hours, and part of this could feel fast-paced or challenging depending on your background. That's okay. You'll learn a lot by sticking through it. And then you'll want to keep learning after this workshop, and I'll point to some resources and hang out a little bit afterwards to answer more questions. So a tiny bit about me. My name is Sage Elliott. I'm a machine learning developer evangelist at plainsight.ai. We do really cool stuff with machine learning, specifically a lot around computer vision and IoT across a whole bunch of different industries. And we're creating tools to make it easier for everyone to kind of build their own models and easily create awesome applications with computer vision to solve problems in, almost any industry. For about the past decade, I've worked either as a hardware engineer or a software engineer, mostly with startups and agencies in Seattle, and then also in Central Florida. So I love making things with technology. You can stay connected with me on Twitter. I'm at Sage Codes. I'm on LinkedIn, Sage Elliott, 2 L's and 2 T's. I love staying connected with people. And if you do build something after this workshop, feel free to tag me in those places. I love seeing what people build. Really, really cool. So about you, normally I'd have you introduce yourself here, but there's like over 100 people in here right now, and that would take a long time. So you can just let me know in the chat real quick, where are you watching this from? And if you want to throw in why you're interested in computer vision, that'd be really cool to hear about too. And I will also share this link in the chat. So if you want to stay connected, I recommend joining the Slack channel. There's an introductions channel in that Slack channel as well. So if you want to introduce yourself and stay connected with other people here, you can do that there. I really miss doing in-person events and actually meeting people and staying connected. So that's kind of the best way I found right now during all the virtual stuff. Seen so many cool places. I saw Bellevue, Washington, close by. I'm in Seattle, so super close. Texas, Virginia, Canada, super awesome. Someone else is in Seattle. Woo! Portland. I'm actually going to be in Portland soon, I think, which would be cool. Madison, Wisconsin. Awesome. It's always cool to see just where everyone's watching from. That is one cool thing about doing the virtual workshops. It's just how many more people you can reach and connect with. So I do miss doing in-person ones, but it is awesome to reach more people. Someone just said Singapore. Super awesome. So I'm going to share the link for the Slack channel again if you want to join it. Oh, so someone asked about where the recording will be. Great question. I'm going to put the recording on our YouTube channel. So I'll try to email it out as well. But if you do want to go ahead and look at the YouTube channel or subscribe on there, you can get notified when it goes up. Cool, another Seattleite. All right, so a repeat just for anyone who came in while we were doing those introductions. Again, you don't need to download or install anything crazy. You just need a modern web browser, a Google account to save the file because it's Colab, which is a really cool tool made by Google. We'll look more into this when we get to the code section. And then really it's just signing up for the data annotation account. Again, no card or anything required. Just sign up so you can see how to upload images and use it to annotate your own data set. So you will be able to build your own model after this. All right, so what is computer vision? It's a very big field, but really I would just boil it down to how computers gain understanding from images or videos. And there's a whole bunch of different ways of doing that. There's other types of data as well. So someone was talking about, well, we were getting started about audio, right? So again, you've probably seen audio visualized somehow as wavelengths. I think it's called I always get it confused with another word. Pretty sure it's called a spectrograph. And so you can turn these audio wavelengths into essentially video or images and do things like classification or detection on them for different sounds of words. So here's a little example I like to show of computer vision happening. So you can see it's detecting all these trucks. It's drawing red around them. It's drawing a square. It's also drawing the pixels over where they are. And then there's a moving truck, and that's green as it's moving. This has kind of a different, another layer on top of just the detection to see like, this truck is moving across these pixels. So I'm going to paint the color green instead of red. And if you're doing this type of work, this is called instant segmentation, where you're drawing actually pixels over the actual object itself. And then if you're doing just the box, that's object detection. So you see, you're classifying something. In this case, it's a truck, and you're also localizing where it is inside of an image. And I'll talk about both of these. Actually, we'll learn basically how to do instant segmentation models and object detection models tonight. They're very similar. It's just a different way of labeling, and then you choose a different model when you're training. Someone said, interesting that the boxes around the truck seems to waver slightly. Oh yeah, so if you're looking at computer vision models and it's running on real world data, that a lot of things jump a little bit, because every time there's an image, in this case, let's say you have a video, which is a sequence of images, and you're running object detection on it, it doesn't know it didn't move. In this case, we're not telling it it's not moving. We're not saying draw the rectangle in the same place. It's running the model every time and giving us the best estimation of where you think it is. So it's not always going to have the exact same result. You can see it's very close. They're not moving a lot, but it gives slight variations in the estimate, especially if things are moving around, then it's really going to jump around and change size. So that's a really good observation, but that's why it's happening, because if we knew these were going to be stationary, we could just draw a box around them and say there's a truck there. But instead, we're telling us a model to give us essentially an estimate of where it thinks the truck is. And that's going to change very slightly frame to frame. So why I love computer vision, so many people talked about all these really cool applications today, right? And I think that's one of the coolest things why I love it. That it's a really amazing interface into the world. And there is already so many things that we're doing today with it that's just awesome. So we'll talk about some of those use cases. And I saw someone ask if I can define instant segmentation. I will go through instant segmentation as well as other types in a minute. So we will kind of tackle what's the difference between object detection, classification, instant segmentations after we talk through some cool use cases. So who uses computer vision? Pretty much like, well, more and more companies are using computer vision across multiple fields. There's so many different ones and so many different ways of using it. We'll just talk about a few that maybe you've seen or heard about. So we have Amazon. I saw there's a couple people in Seattle here, and I forget the other states where there might be some of these stores, but has anyone gone or been into an Amazon Go before? It's a kind of like a convenience store, but it uses all computer vision to track you when you walk in. And then you pick up items, and it uses computer vision to track the items you picked up and associates that cost with you. and then you just walk out of the store. And the first time you do it, it feels really weird. It felt like I was stealing because I didn't have to go through this checkout process. But it's actually been really nice, especially right now during COVID, where I could go in, I don't have to stand in line with people. I don't have to interact with someone if I don't want to. I can literally walk in, grab something and go out. And it's actually kind of cool. It does feel weird. Someone said it feels creepy. It does feel really weird at first. I don't know, maybe I've just gotten used to it where, you know, because I've been going to them more, but I thought that was like a really interesting application. And there's just more of these things popping up in retail now, which I think is really interesting. They're also working on delivery robots, self-driving cars. They bought a company about a year ago called Zoox, product listing. So a lot of images get uploaded to Amazon. They need to make sure that they're appropriate for the product. So they can use computer vision to look at those. And Google, you might have used like Google Photos. You can search for dog in your Google Photos and it'll bring up all the wonderful pictures of dogs you have in your gallery. YouTube content filtering. There's so many hours of video uploaded like every minute or whatever to YouTube that, you know, to scale up looking at it or filtering it, you really have to use things like computer vision. And again, self-driving cars, they have Waymo, Tesla self-driving cars. They're really relying all on computer vision too. So a lot of other self-driving cars use sensor fusion and use other things like LiDAR or radar, and Tesla's really all in on the computer vision only aspect. Facebook, you've probably seen like face tagging, automatic capturing. And then I want to talk about a few other use cases that aren't like the giant big tech corporations. Like these are ones maybe we've seen or used at some point. But you also have fields like agriculture, where you can do things like crop monitoring and animal monitoring and livestock counting, construction, site monitoring, which is a big deal for monitoring for safety. There's a lot of applications around safety, you know, warehouses and stuff. Are people in areas they shouldn't be? Are they, you know, carrying stuff correctly, climbing shelves? I saw a company working on self-driving tractors, which I thought was really interesting. Manufacturing, again, like if you were here earlier, that's how I said I got interested in computer vision, was actually doing quality assurance in manufacturing, making sure that a product or a piece is good enough before, you know, you send it out or before it goes into the next step. Measuring throughput, supply chain, oil and gas, leak detection, and again, like safety for workers is a big deal in a lot of industries. Healthcare, you know, X-ray diagnostics, you've probably seen pictures, or maybe you haven't, but you might have seen like things trying to automatically classify COVID or looking at X-rays to assist a radiologist, you know, make better decisions. And then MRI scans, I've seen it used in medicine research, which is really cool. And then I want to ask you, what's a cool field that I didn't mention here that you've seen applications for computer vision? This is by no means all of them. There's so many I didn't really talk about, like the, you know, the rest of retail. We were talking about drones earlier that you could use for, you know, wildfire detection. Really, there's like a ton of really cool applications. Marine life. Someone said robotic babysitters. That sounds fun. I've seen people use it or making products to monitor, right, like people in assisted care living, where if they fall off their bed or fall down or something, you could have a computer vision system automatically notify someone, which is really cool. I think it's awesome, all these applications where, you know, like if you can actually like save someone's life, that's amazing. Someone asked, what is the I think the most popular embedded system for computer vision? Like for a product. Someone said NVIDIA Jetson products. Probably. I feel like NVIDIA has a lot in that market, which is awesome. They have a lot of really cool products too that you can choose from. So there's a little bit of scale. Like if you're just going for a hobby aspect, you could look at the Jetson Nano. We can also do stuff on a Raspberry Pi. They don't have the GPU, so you really have to be careful with how big of your model is. But you can also get things like the NVIDIA Compute Stick or a Google Coral TPU that you can plug into Raspberry Pi, and then you can do processing on those too. But I do feel like the ones I've seen the most is Jetson products. Someone said robotic vacuum cleaner. Reading stuff from a chess book. There is a lot of cool OCR applications, and that's one I didn't mention here. OCR is object character recognition. So reading text, again, someone talked about it earlier as well, where you could read text from a document, you could read license plates, a whole bunch of different applications for that. Street signs. Someone said ball tracking software for sports. Oh yeah, that's a really cool. Oh, what did I say? I meant to say optical character recognition. What did I say? Optical character recognition, OCR. So the ball tracking one's really cool for sports. I've seen a lot more sport monitoring stuff, measuring how people are running, how people are playing. That's really cool. I'd be interested on like seeing people use that for insights as they play, like changing their strategy. I think that would be really interesting. I don't know, I haven't seen anyone actually do that yet, but that seems really cool. Right, so moving on. So computer vision and deep learning. So computer vision isn't always tied to deep learning. There's a lot of different image processing techniques you can use from libraries that don't involve deep learning. For example, some very basic example you've probably seen before or heard about is a green screen. If I had a green screen behind me for like a movie or something, I can say, hey, I want to replace all these green pixels with this other image or something like that. That's kind of a form of computer vision, right? Like a very basic form of image processing. But in the past decade or so, pretty much everything you hear about and all those applications we talked about, chances are they're using deep learning behind the scenes, because when you use deep learning to tackle these problems, it can really understand and create solutions for much, much more complex problems. And other interests will go way more in depth into deep learning, but just kind of give you a very, very high level overview so you understand why we need a data set and like why we need to label it and why we need to train it. So you have deep learning, we have this machine learning model that we're going to give our training data to. And in this case, our training data is going to consist of images and some sort of label tied to those images. So if you're doing classification, the common example is if you were to classify images between dog and cat, we would give dog and cat images to our machine learning model with the labels dog and cat accordingly, right? So I would pass an image of a dog. I would say, hey, this is a dog. You should try to learn the features going on here so you can learn how to make a prediction on a new image you've never seen and understand that it's a dog. And it's really hard to understand, right, like how you would do that without machine learning. So if you were to create rules that make up a dog or cat, it's really tricky, especially if you're doing things like at different scales and sizes. It's really, really hard to do. I don't think you'd be able to do a good job with it with just like doing if statements, right? Like trying to measure corners of ears and snouts and stuff like that. But deep learning does a great job at kind of understanding images. And specifically, there's a kind of neural network called a convolutional neural network. And I'll share this link in the chat. This is called TensorFlow Playground, which is a really cool kind of visualization of how a neural network works. Don't worry if it looks confusing or anything. You don't need to know that in order to kind of do the stuff we're going to do and train with Python, but it's a good resource to go look at if you've never seen it before. And then I shared a link for a cool visualization of a convolutional neural network, which is a special type of deep learning model that looks at images and will learn how to understand them. So like the dog and cat example, we would pass in all those images. It would then learn from that, and we would look at some sort of metric while we're training. And we would say, hey, cool, we think this model is going to be good enough now. Then we'd give it a new piece of data, in this case, an image it's never seen before, and then hopefully it would return the right prediction. And so we'll talk about the different types of computer vision, but essentially the ones we're going to talk about require some sort of label going into it. So for object detection, you have a special type of label. For instant segmentation, you have a special type of label. And we'll talk about all those differences in a second. And then just a quick note on transfer learning. So with most popular deep learning frameworks, you can load in these pre-trained weights. So that means that someone already went through the trouble of training a model on like thousands of images for thousands of hours, and it can work pretty okay for maybe detecting like whatever was trained on. So a common one for object detection is a Cocoa dataset. There's 81 classes in there. It has things like people, cars, etc. And sometimes using that pre-trained weight can even work for your application. But like someone was asking about training data, most of the time you need to collect data in kind of the angles and lighting conditions and stuff that you might be seeing it in. So you could use this as a starting point, collect data, and then you want to take that new data, label it, retrain the model, even though it was trained on maybe stuff it's never seen before. So let's say you were doing a object detector for dogs, and I think the Cocoa dataset might have that, but let's say it didn't. It was only trained on like people and cars. Well, it turns out that even if you're retraining a model to look for something completely new it's never been trained on before, you can use transfer learning, and you just think of it as it's not starting from zero. It already understands how to like put shapes together and stuff like that. And then you're really just fine tuning it to fit on your data set. So a couple links of the common data sets for this is the ImageNet data set for classification, and then the COCO data set for object detection and instant segmentation. So without transfer learning, you would probably need like thousands of images and a lot more time to train your model. But you're going to see today, we're only going to use a couple hundred images and actually build a decent object detection model for geese is what we're going to do today. So some types of computer vision, again, it's a very big field, so we won't talk about literally everything, but some of the common types that you're going to see, and probably the most common types, so you could start kind of putting together and solving your own problems. We have classification. We talked about this example, right, when I was talking about deep learning, where you're associating a label to a whole image or a very specific cropped part of the image. So in this case, I trained a deep learning model to predict the breed of a dog. And when I fed it this image, it said Labrador Retriever. And I fed it, thousands of images of all these different dog breeds. And then I could give it a dog breed and get some sort of prediction return. Most tutorials start here and cover classification really thoroughly, but I think it's really powerful and awesome to kind of almost skip ahead and get to object detection, which is something you can totally build, even if you're new to the industry. But that really is where a lot of power comes into play, because classification is great for certain use cases, but it kind of quickly becomes limited. Like, let's say we wanted to count how many dogs were in this image. We can't do that. It would just kind of predict if there was a dog or not, or in this case, the breed. If we had a Chihuahua in the back of this image, it would probably really confuse the classifier, because we would tell it to look here for one dog and here for another dog. It would just look at the whole image and make a prediction if it was a retriever or a Chihuahua. So with object detection, we actually get to classify and localize where something is inside of the image and on multiple instances. So here there's two geese, right? And we're very confident this is a goose. We're very confident this is a goose. And we're drawing this bounding box around them, or this rectangle. And we're saying we're pretty sure they're within this box. And now we could also do things like count how many are in a room or in our camera feed. That already gets you to a lot of applications. So I've seen a lot of people using computer vision to count how many people are in a room, right? Especially during COVID, if there can only be 20 people in this room or something like that, you can use object detection, can already get you there, say, hey, I counted 20 people in this room, and send some sort of alert. You can also do things like calibrate how your camera is situated and understand how far away they are. So you can see, like, if these bounding boxes were overlapping and we kind of knew the angle of the camera, we can make an estimate of like how close they are for social distancing, for example, or if two objects are interacting with each other. And we're going to make this today. We're going to talk way more about object detection. You'll see how to make this in a Python framework today and label for it. We'll also talk about instant segmentation. So kind of like the truck example, here's just another example of it where it doesn't only draw a bounding box of estimate of where the object is inside the image. It's actually drawing pixel by pixel what it thinks or where it thinks the actual object is. And this is useful if you need more precision over interactions between other pixels, or often if you just need a more accurate model. It depends on what you're trying to do, but a lot of the times a instant segmentation model will be more accurate than a just plain object detection model, even if you just needed the outcome of object detection. But you can also do things like in this case, we're measuring water in this bottle, and we could then do like a volumetric calculation saying this many pixels overlap with the pixels of the bottle, so it's this full. Or you can imagine if you had a limb or fingers or something like that, and you want to see when it's touching in another object or a key on a virtual keyboard or something like that, you could use instant segmentation for that. So if you just need more precision, either to do some sort of pixel calculations, or if you need more accuracy overall, often you might choose instant segmentation. But we'll talk about why maybe you won't want it sometimes too. So feature points, someone had mentioned doing pose estimation, and that's what feature points is great for. It's also great for face applications. So reading like expressions on face. You can say here, it's predicting body poses of these people doing yoga. So it went from one pose here and then changes classification just based on how these feature points are laid out and kind of how they map back to the body. So like the angle of these arms in relation to the head and the rest of the body, you can do things like predict poses. And like I said, you could do this for faces. So it's very common. You might see an application of computer vision on a face. So it might be drawing feature points around the mouth and eyes and eyebrows, and you can like tell when someone's angry doing that. Generative deep learning, we also mentioned this previously while people were joining. We talked about how I saw an example of someone using GANs to generate artificial teeth for people who needed like a new tooth. And it's really cool. It's a really cool industry. I won't go too deep into it, but just the whole generative deep learning industry is really cool. This Medium article talks way more about it. And then here's actually a project I worked on with someone where we generated original architecture designs using GANs, which is a really fun project. And these images on the side actually came out of that project. They don't look like buildings yet at all, but they look like really cool space art. So I saved them because I thought this looks really cool. And it's really fun. If you're just looking for something kind of fun and you want to go down that rabbit hole, I totally recommend it. Building a GAN and feeding it images is just really fun, and seeing what comes out. So I, at one point when I was newer to it, I fed it a whole bunch of images of cats, and the cats came out looking really creepy, like they looked like demon cats, but it was really fun to see the results. So out of, actually real quick, out of all these ones we just talked about, which one would you want to see? Like, let's say I do another workshop on a new topic. Which one would you want to see next, besides object detection, because that's what we're doing tonight? Someone said GenerationGANs. Cool. I've been thinking about doing some more GAN work recently, so that might work well. Someone said demon cats. I'll have to show. It's on my like LinkedIn or Twitter or somewhere. I should put that in here next time or have a link to it because it's pretty funny. Pose estimation, that'd be a good one too. Yeah, hopefully at some point I'll get to kind of creating all of those. So I'd love to do one on pose estimation as well. I think that's really fun and kind of opens up new applications. All right, so choosing a model, there can be a lot of different cases for different models and ways to tie them together. But when you're getting started, just think, what is the problem you're solving and what's the outcome you're looking for? So do you really just need that bounding box? Do you need more pixels for the instant segmentation? Are you doing pose or face estimation where you might need those feature points? Or do you just need classification? Like you just want to look at a whole image and tell you if something's in it or not. Like, is a dog present in this or not? In this case, you can see there's a mouse interacting with food, and when the food's on its face, it's saying feeding, and then when it kind of leaves it, it classifies it as not feeding, and that's doing interaction, right? Just like we were saying, like if this pixel interacts with this other pixel, then that in this case is classifying it as feeding. And there's a couple other reasons for choosing a model I'll talk about in a second, but that's when that comes down to deploying it. So there's some things you want to think about, like speed and how hard is it for hardware to run. We'll talk about that, I think, after this slide. I just wanted to give you a little bit more information about object detection. And really, again, I'm going to link to this article in the chat that goes way deeper into it. But just at a gist, what you're really doing is training a model to find kind of proposed regions where it thinks that object might be in the image. Then it's going to run a classifier around it. So if you have done things like computer vision with classification, you can actually see that when we choose our object detection model, there's a backbone to it, which is often a common classification algorithm. So the one we're going to use today is called ResNet50. It's really common, and it'll run a classifier around the regions, and then it'll calculate an estimate for object detection. That's what's going to give us this kind of final output of the bounding box of where an object is. And again, that article goes like way deeper into it. That's just a really high level kind of gist of what's going on. And then so popular object detection methods, and this is where kind of like this can come down to like other reasons why you might choose a model over another one. So you have a single shot detector or single shot multi-box detector, abbreviated to SSD. It can do object detection, so it can draw those rectangles around those objects, and it is known for being lightweight and fast. You have YOLO, or you only look once. It also does object detection. It's also pretty fast. And there's like always new versions coming out, and I never remember which one's like technically the best or whatever. in terms of benchmarking. In my head, I could be wrong now. In my head, it's always SSD is kind of like the lightest model, but you might be sacrificing some accuracy. And then you have mask RCNN, or a faster mask RCNN. It can do object detection. It can do the image or instance segmentation. And then it tends to have a much higher accuracy, but it's also slower to run. So we were talking about drones earlier, deploying a Model 2 Raspberry Pi, for example. Chances are it probably won't run a mask RCNN very well unless maybe you have a TPU or something in there that you can run it on. But it probably can run a very light single shot multi-box detector object detection model. And then we have what we're going to use today is called Detectron 2. This is a really cool library that has a lot of these built-in methods that we just talked about for doing computer vision. And it's kind of a wrapper around PyTorch. So they use PyTorch, but it's kind of a wrapper where it has some pre-built functions that makes it really easy to do things like object detection that is showing here. And then it'll show feature points in a second. So you can do feature point training in this. And then they even have this special thing called dense pose, where you can create 3D like models based on how people are standing, which is really cool. So if you're into like game design or animating, I've seen people using this to kind of create and animate those models. We have instant segmentation happening here. So, it's not just drawing rectangles around everything. It's actually just painting the pixels where it thinks something is. And again, you can see it's not perfect, right? Like this table is out a tiny bit and you'll probably see it moving around. Just like someone said, why are things moving? It's because it's, it's drawing an estimate and it's making its best guess. And it's not always 100% perfect there. And then we have, I always forget the word for it, but it's where it colors every pixel. I think it's Semantic segmentation. And so here it's, every pixel is being filled in. So it's classifying this as cabinet, wall, ceiling, wall tile. It has a whole bunch of different classes built in. And so this is actually just running like that pre-trained Cocoa dataset model that we can use for transfer learning. It's really cool. So, and it's awesome to kind of get started and start building these models and actually really powerful. So we're going to use this today and use it for object detection. And I'll show you how to switch like one line of code out. You could do instant segmentation. Right before, so we're going to get to the hands-on labeling in just a second. I just want to mention, so we've talked about like labeling and training a lot, and those are often talked about the most. Usually it's just talked about machine learning the most in courses and stuff. And when I was learning computer vision, this might have changed now, but all the courses talked about training models, but they never talked about like creating your own data set, especially for things like object detection. So I really hope that this will kind of break that barrier down that maybe some people have felt as well. But I just want to mention a couple other stages that often happen if you're deploying for, like a business application. You have device management, so you have to manage, where your model is running. You might also be collecting data from cameras at the same time on those same computational resources. So for example, running on a drone, how do you manage like deploying a model to a drone, taking that data from the drone, potentially even relabeling it to create your model better, like we had talked about. You have data collection, so managing data from sensors, in this case cameras, but it could also be creating data sets or like web scraping. Then you have the labeling, the machine learning, so selecting the correct model that's going to work for a use case and then training that model. And then you have deployment. So once you train your model, what do you do with it now? You could run it on a video you have locally, but oftentimes you might want to deploy it somewhere where you could then connect like a camera stream or a drone to it, pass an image and get that prediction return. And then sometimes there's another layer where once that prediction is returned, what do you do? Is it to send you a text notification? Is it to do something like object tracking, counting things? It's kind of like another layer after deployment or during deployment. And then often you want to repeat the cycle for what's called continuous machine learning. And this is going to avoid what's called model drift that can happen in some instances. And so just one use case for that, like we talked about going to Amazon Go, right? And like having these computer vision models look at you in the store. Well, if we trained our model in the summer and everyone was wearing shorts and t-shirts and maybe baseball caps or tank tops or something like that and flip-flops, and then we ran our same model that was trained on the data in the winter and people are wearing completely different clothes, like lawn jackets and maybe giant hats and scarves and stuff, chances are our model that was trained on the data during the summer is not going to work nearly as good on that winter data. So we often want to keep collecting data even as we're running our application and then relabel it or label it and then retrain our model with more data. So Typically, more data and more variation, the better. One example too, even is like if we were training a model to detect geese and all the data was geese in a park with green grass, and then geese happen to be in snow, and we were trying to detect them in snow, chances are our model just wouldn't work as good segmenting out the geese from snow because it wasn't trained on it if it had never seen it before. So it's kind of like, training a model, you really need to think about the different variations you need to pass in and show, you need to show it all the stuff you're looking for in all the different like conditions that you're looking for it. Otherwise, it just might not work super good. And so you can keep doing that kind of through all the seasons, for example, and then your model would hopefully continue to function great. Style trends might change too. So if people are wearing new clothing that it's never seen before, it may not perform quite as well. And then right before we get into the hands-on labeling, so we're kind of building a platform out to do all those things in one system and like one interface, because right now it's really hard. You could be doing parts of this in one cloud service, parts of it locally, and tying it all together can be quite hard. So if you're interested in seeing like a demo of that, if you happen to be working at a company where this might be useful to you, you can fill out the contact form there. And we also just recently launched on Google Cloud Marketplace. So if you need all of this in your own instance where you're actually owning your instance there, you can deploy it in like a private cloud, which is pretty cool. And then on to the image labeling side. I'm going to pause real quick for questions and post this link again in the chat. So if you weren't here before, you'll want to sign up now for this data annotation tool, and then we'll walk through how to use it, how you can use it on your own data, and talk about the problems you might have while labeling and how to speed that process up for you. But I'm going to pause for questions. So I know we kind of covered a lot. It was like a crash course in computer vision and a whole bunch of different applications. Does anyone have any questions? I probably missed some in the chat before as well. I'm going to scroll up and see if there's some good ones I missed too. Oh, someone said, any thoughts on the transformer architecture in computer vision? So if you don't know what a transformer is, it's kind of a new architecture, or I don't know how new it is. It's making waves in the computer vision, and specifically really big waves in the natural language processing industry. It's a kind of, instead of using a convolutional neural network, you can use a transformer, or you could still use them combined a lot too. So you might use a transformer to, or sorry, you might use a convolutional neural network to kind of distill your image to a smaller size that you can feed it to a transformer, and there's really cool results on it. So I mean, my thoughts are like, I haven't done a ton with it yet, but just seeing the results, they seem really, really cool. There's a lot of awesome results I'm seeing in papers and stuff like that. And I know we've used them in certain applications. I personally haven't done a ton with them myself, but they seem really, really cool. And I think there's some really good applications that they just like probably make way more sense for. Someone asked, is instance segmentation any different than segmentation or synonymous? Great question. So the instance segmentation is kind of drawing around these specific instances of an object. You also might hear it as image segmentation, but there's also, I'm blanking on the word, semantic segmentation. So we didn't talk about that. Semantic segmentation, instead of classifying each individual object, it would just paint one class over it. So like this, we know in this case that this is one detection of a bottle, this is one detection of a bottle. There is something called semantic segmentation where it would just say, all these red pixels are bottles, but we wouldn't know they're individual objects. So it depends on how people use it, but segmentation I feel like a lot of stuff I'm seeing now is often a instance segmentation, but they could be talking about semantic segmentation, which would just mean that it's classifying all the pixels as something together as kind of one blob. Someone asked, any drawbacks on using smaller data sets with deep learning? Some data sets are hard to come by thousands, AAK medical. Yeah, so I mean, the drawbacks are often your model may not be as good, but you can get started with smaller ones and see how well your model performs. Kind of the rule of thumb is more data, the better. And there's also really interesting stuff happening in that field that I actually am really excited and kind of passionate about is something called synthetic data. So if you can't get all these images, there are ways sometimes of creating fake versions of those images that you can actually use to train a model pretty well. So Unity, which you might know as like the game engine, a lot of games are created on Unity. It's like a 3D game engine. You can create stuff in there, train a model, and it turns out that sometimes that actually works really well for training a model to work with real world data. There's also a field that I'm kind of interested in, and I built some kind of like personal tools around of like creating synthetic data in kind of a 2D format. So instead of creating something in Unity, you can actually paste stuff into other images. I actually have this up. So I did a talk about this before. I'll put the link in the chat. But this actually talks about using synthetic data to kind of overcome data limitations. And so like one example is, right, I talked about how you need all the variations that you're looking for. Well, I trained this Goose detector and it did a great job at detecting geese in parks. But then if I ran it in my living room, it was like pretty confident I was a goose. And that's crazy, right? Because like I'm not a goose, and at least not that I know of. And so what I did was I actually used synthetic data where I then put like geese in these backgrounds containing people, trained it, and then it did a really good job of not detecting me as a person anymore. And you could also, potentially throw in just images into your data set without the synthetic stuff to help as well. So it might mispredict a person as a goose and then adjust that during training. I see some other questions. I'll just do a couple more and then we'll get to the labeling part. And again, I'll be hanging out afterwards. So if I do miss your question, I'll try to get back to you on it. Someone said, I'm new to ML and DL. What network models for segmentation, also data set, image size matters? Lower resolution versus high resolution. Good question. So the data set resolution, you can play around with it and see for your use case, but often what happens is during training, at least with convolutional neural networks, you're actually condensing those images down. So a lot of times you don't need super high resolution, but that does depend on what you're looking for. So if you're trying to do classification on a small tumor in some sort of medical image and you don't have high resolution to see it well enough, you would need a high resolution image. Or you would need to crop out that part and make it smaller or something like that before you feed it in. But a lot of times for, in this case, doing something like geese, we're gonna see we don't have super high resolution images. They're actually resized to be like 600 pixels or something. And it does a really good job of understanding it in a high resolution video because it's also kind of compressing that video down when it's looking to make those predictions. All right, so I think there might be some ones I missed. Again, sorry, I just want to move on for the sake of time, but feel free to ask them again later if I don't get back to you. And just one more time, I'll share this link in the chat. It's going to be the data annotation tool we're going to use today, and I'll walk through all these features, and then you'll be able to build your own data set after this workshop and create an awesome model. Someone said, I sparked an idea for them. I could build a model to identify cigarette butts on the ground. Yeah, I've actually seen people do that model and actually use synthetic data creation for it. So like if you took cigarettes and pasted all on images in different backgrounds that maybe you couldn't acquire that data for, that's a cool application. Oh, someone said syringes. I've thought about that too, where it's like, that would be an interesting project, creating something to detect, something like that. All right, so I'm now in the data annotation tool. Right now, you can see it still has the 6-skill URL. That'll probably change, and it says sense. That's going to change to just plainsight as well. But the rest of the functionality really shouldn't change too much, except for we're adding more features into it. So you can see some stuff's grayed out here. What I talked about, how we're creating all those different steps to integrate in one platform. This is where we're doing it at. But today we're just going to use the data annotation part, and then we're going to export our data after we annotate it, and then bring it into a different environment using Python and running code there. So I'm going to hit new data set. And oh, sorry, I forgot to share one more link. So if you want to follow along with the exact images I'm going to use, you can do so here. That's just a Google Drive link, and you can download those. There's a folder that I think is something like object detection and instant segmentation. And you can download just those, and it's like 8 images. And I'm just going to go through different variations of labeling, so you'll understand what to do when you're building your own model. So if I go back here, I'm going to start over. I'm going to hit new data set. And you want to give your data set a name. This should be meaningful. But in this case, I'm just going to call it workshop. But it would be whatever you're actually trying to do, cigarette butts or something like that. And maybe even want to add in like segmentation or object detection, so you kind of know what type of label you were doing in that specific project. So I'm going to hit save and continue to sources. Now, sources is where you get to connect a data source. In this case, I'm just going to upload local files, and that's why I shared that Google Drive. If you want to download those images and follow along, you can. But I also encourage you, if you have images on your computer, upload a few of those images and play around with the labeling. Like maybe how would you label people in this specific instance, or if you have photos of your dog, how would you label your dog? And try around some of the kind of AI-powered features I'm going to show you and see how they would work on the type of data that you have. So in this case, I'm going to hit upload local files, but we can also connect to Amazon S3 buckets and Google Cloud Storage. So a lot of times, really in a commercial setting, you're probably saving your data to an S3 bucket or something, right? Like maybe your drone is sending images back, or when it lands and connects to its charging dock, it's uploading the video to an S3 bucket or Google Cloud Storage, and then you want to import that data in here and annotate it. You can do that. So it'll just prompt you for the name, and if it's secure, the password and stuff like that. But for this example, I'm going to hit upload local images. Oh, and just one more feature too. So if you're connecting to Amazon S3 or Google Cloud Storage and you import a video file, it'll actually ask you how you want to break it down. So you could import an MP4 and it'll say, hey, there's a video in here. How many frames per second do you want me to break this video down so you can label it? And that feature is not quite here on the upload local files, but it's coming soon. So here I'm in that folder, and I'm just going to upload these examples, and we're just going to walk through some different variations of labeling, so that when you're creating your own model and creating your own data set, hopefully you have the knowledge of how to do that afterwards. So I'm going to create kind of several different types of labels and go from there. So it's uploaded. By the way, you don't have to wait for all of them to upload to go to your label definition. So I'm going to go to label definitions, and this is where we should know at this point what we're trying to create, right? Like, do we want to do object detection? What's the end goal of our model? Is it to do we want to count how many geese are in the frame or people are in the room or something like that? Do we want to do instant segmentation? Do we want to do feature points? Because you can choose the label type just in this drop-down box here. So by default, it's rectangle. You have polygons, feature points, text. We even have some other ones like for classification that you can use as well. So I'm going to make a few examples here just to show different types of labeling. So I'm going to have one called Goose. I'm going to leave it as a rectangle. This color is really just for you as the labeler right now. If I know the geese are in a green background and I really want my labels to be visible, I can choose like this dark blue, and then I'm going to hit save here. And you'll see that now I have this label kind of in my project. And a quick note, so you might see this area for auto label. We're going to come back to this. I'm going to show you how to use this, and it's going to pop up in a different interface. But I just want to mention that you can set up auto label here, and it's really powerful feature. It's exactly what it sounds like. It's auto labeling your objects for you, but we'll talk more about that in a minute. So I'm going to make another one called Goose Polygon, and I'm going to, just so I can show you the difference between labeling for object detection and polygons. And again, I'm going to change this to kind of a brighter color that's going to stand out more on the green. And then I'm going to show you an example of creating labeling cars kind of in traffic, and the green's actually good for that. And I'll create one for cup. We're going to see an example of that. This is also going to be a polygon. Green is good for that as well. And then I have one more example. It's just going to be a PCB, a printed circuit board, a common thing kind of in manufacturing, and similar to kind of what I was doing when I first got started in computer vision and PCB damage. So we could create something to look for a printed circuit board and find the damage on it. I'll have that as a polygon as well. So you might not always want to mix all these different label types. Like often it's pretty common to just kind of stick with one in your project. And I would suggest so when you're starting out, because otherwise you kind of get in this interesting area of like how to train models or multiple models and tie them together. Just want to quickly mention that. So normally I probably wouldn't mix a ton of different types together. And someone was talking about feature points. I don't think I have a good feature point example in this data set, but I'll just make one just so we could look quickly. And this is where you want to know how many feature points you're labeling. So if I was doing a hand, and one example I've done is like labeling just between like the tip of the fingers to the base of the palm. So you could actually see like, distance or some sort of gesture. You could do like 10. So it'd be like 1, 2 per appendage. So I'll just show this example as a little bonus one. All right, so we have all of our labels made. We also have this labeling instruction area, which is super important for like if you're working with a team or you're not the industry expert in whatever you're labeling. So for example, if I was labeling something in healthcare and a doctor wanted a model that would predict a certain type of tumor or something in an X-ray, chances are I wouldn't know what I wouldn't know what that looks like. So I would need them to tell me and provide examples of it. So ideally, you'd have them do some of the labeling and then provide like detailed instructions of what to label, but also like provide images of an example of a good labeled image and a bad one. So you can embed all these here. We're going to skip this for now, but you can just type stuff out. You could also embed images, and really important when you're working as a team, especially, but also if you're not the industry expert, someone could tell you how to do something and then you can come back and reference these instructions as you label. So I'm going to hit save and start labeling. And here, this brings up my first image. It is a goose. So if we wanted to label it just for object detection, this is kind of the classic way of doing it that pretty much any other annotation tool will have you do it, right? You draw a rectangle. So we select our rectangle label, and then we just draw a rectangle around our goose. And you actually want this to be pretty much as close as possible to the object without cutting it off. So like this would be a pretty good label. This one here kind of went too far down on the bottom. And if you want to adjust it, you just hit escape to kind of get off putting on a new label. Then you can go back to your labels and move them around. So I could come back and fix this. And this would be how we would label this image the traditional way for just kind of object detection. And one really important factor of this is if we had another goose over here, we would want to label it too. For example, if I just fed our model this one goose labeled in this image, it would be really confused about what we're looking for, because it would say, well, it says you're trying to look for stuff in this image, and to me that looks like this goose, but then you're saying you don't want this, or this isn't one of those objects because it's not labeled. It's going to be very confused. So if you have a whole bunch of objects in your images, you want to kind of label all of them. And one exception to that is maybe if they're really far away and you're okay with your model not making the prediction, then maybe you don't need to label that. But if you had a whole bunch of geese here and we didn't label it, it would really throw off our model during training. So now let me show you an example of kind of the traditional way of doing polygons. And the polygons are used for the instant segmentation. This would be the labels that we would provide to our faster mask RCNN to get that instant segmentation model trained. So you have to kind of trace around, and you want to be pretty precise. So you have to trace around the object you want. And just for sake of time, I'm going to speed up here, do a very poor job of doing this kind of labeling. But you can see already, like, this takes way more time than doing the object detection labeling, right? Like drawing the rectangle was super easy, really quick. And this is actually something that's common, like where people wouldn't want to use polygons because it takes so much more time to label. So I want to show you a cool feature that really helps with that. We can click our polygon label for Goose. We're going to enable something called Smart Poly. So you just click this button here, select our label. Now you get this bounding box crosshair, just like we did before. And we want to draw our box right around our goose like we did before. But now it's automatically going to try to snap polygons around it. So this is way faster, right? That took me pretty much the same amount of time to label the bounding box version. So let's go ahead and do it on this goose as well. And purposely, I use this example because it's not always perfect. It does a really good job of segmenting like foregrounds or objects from backgrounds, but you can see that in this case, if I zoom in here, like my eyes have a hard time telling where the goose ends and where the sidewalk begins. So you can see it wasn't perfect there, but the cool thing is this is like almost there. This is like 80% of the way labeled. So again, I can click on my label and it brings up these kind of different nodes where I can highlight one by clicking on it and I can hit the backspace or delete key and it will delete that node, or I can drag them around. So if that was the only part, boom, fixed. I think also it messes up a little bit up here on this white part. And again, that was way faster than manually tracing around really precisely on the Goose. So that's a smart poly feature. And then let me show you auto label real quick for Goose. So I'm going to turn on auto label. Like I was saying, it can come up in a different spot in the labeling tool, but you can also define this right when you're creating the labels if you want. So let's hit auto label. The way this currently works is you can only choose from 81 pre-trained classes, but coming soon, you'll be able to label your own data, train a model, and then tie that model back into auto label and then have it automatically label your data. So if you like, we'll see some limitations of this too, where, like I was saying, if it's only trained on images, directly up front, and then you have drone footage looking at the specific angle, it might not predict correctly on that class. So you'll want to tie in your own data most of the time. But right now, we have all these classes to choose from. And so unfortunately, there isn't a Goose one, but there is a more generic bird class. So I'm going to hit bird, and then I'm just going to hit OK. And boom, it applied the labels. Now, let's hit the submit while this is still active. So you can enable and disable it by clicking there. Let's hit submit. And boom, brings up the next image and automatically applies those labels. And the cool thing is, like, if they're not 100% perfect, in this case, they actually look really good, right? But if they weren't perfect, we could go in and edit it. So we're really kind of getting to this point in the industry where you as the human ideally should kind of just be QAing the data and making sure that your machine learning models are providing the right labels, which is really, really exciting, because data annotation used to be such a time-consuming part of building computer vision models. And I'm going to disable this here, and I'll hit submit here, and then I'm going to show an example of this car. I see some questions, so I'm just going to roll through all these examples and then pause for questions if that works for everyone. So here we have a car, it's a polygon. I'm going to go ahead and start with auto label in this case. So again, you can enable it, hit this little drop down, hit auto label. Now, I know we're on a highway, so I can type in car. I know that's a class. And then I could type in truck because maybe there's trucks on the highway. And I think there's a motorcycle class as well. So kind of just like, I want to detect all the vehicles that I think might be on the highway. And so like right now you see there's just one option, but there'll be more soon. And that's where you can tie in your own labels or your own model. And then we'll hit OK. This will automatically apply the label to the image, just like we saw before. And now I'm going to hit submit. So this would be like if you had a camera, and you're tracking cars on the highway and you want to count how many cars are driving by or something like that. And to label the data, we can turn on auto label. And right now I'm just kind of hitting submit, and it's applying the label. And I'm really just verifying that it's doing what I want to do. And you'll see there's going to be a spot because this is just using a pre-trained COCO model. And it isn't perfect on our data set. Like maybe it hasn't seen enough cars at this exact angle or something. Right there, it didn't apply the label. So we'd want to come in. Now we want to apply our car label. We could use smart poly here again. This looks like a car coming in. So I would give that a little label there. And then I could just label this real quick with the smart polygon. And I'll hit submit. And again, in this frame, it got this car, but it didn't get this other car. And this is a good reason why you want to tie in your own models. And this is something like cars. If you have something much more complex that there isn't a pre-trained model for, then you really want to tie in your own model. And then I'll hit submit again. And now it's now it's working on all these angles. So it's just applying the labels. So one more really cool AI-powered feature is called track forward. And this works for if you are importing videos and you have the sequence of frames that go together. And so what it does is it tracks, you can label something. So in this case, we're going to label this cup. I'll use Smart Polygon to label it. And it'll look at the next frame that's like from a video. So they should be fairly close together, probably moving across the frame. And it'll automatically track where it thinks these objects went. So I'm going to enable it again in this little drop down, track forward. I'll hit submit. And so you see the first one is just a slight shift. So it's like, ooh, not super impressive. It almost looks like it just copied it over. But then the next one, you'll see a much more drastic shift in kind of the angles. And this isn't using auto label where there's a cup. Right now, if a pre-trained model exists for it, you could use auto label for it instead. But the track forward is really for any object, and it'll try to track from frame to frame where it's moving. And it's not trained on that specific object, but it'll recognize what you labeled and try to predict where it moved to in the next frame. So really cool on video data, and if there's if a class that auto label isn't for. Oh, someone said, I saw someone talking about zoom. So you can zoom in by using your scroll wheel. And that's a really great feature. Sorry, I should have mentioned that, because often you will want to zoom in and make some fine adjustments or something to some labels. If for whatever reason, if you zoom way out and really lose your image, move all the way over here, you can always hit this resize to fit button, and this will bring back to the default view. So that's also good to know about. You have some other things like undo, clear all the labels, so we can remove those labels we just had. This button will bring up those instructions. We didn't add any, but that's where the instructions live if you want to reference them just kind of while you're labeling. You can also adjust some appearance. So if it was really hard for us to see something, I've actually used this in some low lighting conditions where I want to label it, but it's hard for me to kind of exactly see where the outline is. This isn't changing the data that your model is going to be trained on. This is just changing it for you so that you can label it better. So there's some other stuff in here, kind of basic tools like that. Just real quick on this last example, this isn't going to be anything special, but maybe we want to label a PCB. We could use Smart Poly, I guess, but we could also just draw four corners pretty easily, right? Because this I actually need to adjust a little bit, and then we could do something like labeling the specific damage, like these scratches in the PCB. And there's a whole bunch of different ways of doing this. Maybe it's better for us to just have two classes of segmentation, have one labeled as a good PCB versus a bad PCB. It depends on how we want to detect the damage in this case. Anyway, let's go ahead and submit our image. Once we've gone through all of our labels or just the data, enough data that you want to train a model on, we can export our data set. But first, I just want to mention real quick. So if you are on a team, and it's very common to be on a team at a larger company, you can go in and review all the labels. So you can go back to your labeler. You'll see this little drop down. By default, it's always showing the pending images because most people are there to label. But you can go look at this submitted ones, and this will bring up all the labeled data. And then you can hit approve or reject. So I could say this looks good. I'm going to approve it. This looks good. I'm going to approve it. This looks bad. I'm going to reject it, and we'll go in a different bucket. And then when we export our data set, which is what we'll do now, we'll hit export data set. You'll see there's an option right now if you scroll down where it says approved annotations only. That's the default because that's most professional clients and stuff will have reviewers. And so by default, it's only the approved annotation. But if you're working on a hobby project and you did all the labels yourself, you really probably want to do all the submitted annotations if you didn't have to go back and review them all, right? So just check this box, submitted annotations, and this will export all the data we've labeled, even though we didn't review it. And then on the left here, we have all the common types, or most of the common types of kind of data formats for computer vision. So you have create ML classifier, that's Apple's version, Apple's format for classification. Create ML object detector. We have Cocoa. This is probably, I would say, probably the most common format you're going to encounter. The cool thing about it is there's a lot of pre-built functions in most of the major frameworks where it'll know how to read in a Cocoa data set. So you don't have to do as much work. So this is a common factor of choosing something really is is there a pre-built function? Do you know how to work with this type of data? And it's really just a different way of organizing the data. I'll show you in a second what it looks like. And then we have these other options. I'll talk about this when we train our model, but it's common to have what's called a train, test, and validate kind of split between your data set, where the majority of the data sets used for training. And then these are two different types of tests you can do while training. And I'll talk about those when we get to that. So I'm just going to hit export here for Cocoa. And this is what you'd want to do. So after this workshop, if you want to go label your own data set and then bring it into the Colab notebook, you want to go in here, hit submitted annotations, and then hit this Cocoa format, and then hit export now. And then you'll say export completed. It'll send you an email to the email you signed up with and have a download button there, but also push notification will show up here. It can take a second. So just for this workshop, I'm going to refresh it. And it should show up immediately if you refresh. And then you can see export available, hit download export. This will download the images and the Cocoa data annotations that you labeled. So if I open this up, zip file. If I open up this train, this will look crazy. Don't worry, you don't need to know how to read it. We're going to use a Python function to read it in. But just to give you an idea of what the data annotation looks like, when we're done with it, it looks like these crazy numbers. And these all get associated back to an image. And in this case, we can see this is a B box for bounding box. And it's really just 4 coordinates of the rectangle. Someone asked, does Sense do the train test split? Yeah, so it has that option to do the train test split, and it's enabled by default. So most of the time I do like an 80-10-10, where 80 for train and 10 for test and 10 for validation, which again, I'll talk about the difference between like test and validation when we're training our model in a minute. So we're almost there too. So, but this is what the annotations look like, and we will export it, or we'll import this in and train a model with it. Cool. So I know that was a lot. Any questions on data labeling? Someone asked about class balancing. We have some features I know that we're working on. I don't know about the timeline for that will actually help with class balancing or imbalancing as well. So that could be like if you've never heard of that, like we have way more images of a positive result of COVID versus a negative result, and the model gets kind of overfit and to these positive results. We're just one kind of quick example. But yeah, there's going to be some tools coming out around that, which I think is really cool. Oh, so I did mention about the pose, and I never showed that. And again, there's not a person in here, so this will be kind of weird. But essentially, we have our feature points, and then we would draw. So let's say this was around the cup, and we're saying feature point 1 is the handle, and 2 is this other part of the handle. And we're just going to really, again, this is weird because it's a cup and it should have been like a hand or something like that. But you can kind of see that the gradient of these dots change to show from like the first point to the last point. Just showing, because someone was talking about feature points and they wanted to do an application with it. And so you can create a feature point label and then label your data in here. This is kind of a poor example of it. Any questions on the labeling side of things, though, before we get into the code? Did anyone think the features were cool, features they would use? Has anyone done data annotation before? So I think also, I feel really spoiled now because now I use this tool all the time. And like even before it was released for all my data annotation, like I didn't want to do polygons before because manually drawing them is really annoying. But using like this smart polygon selection is awesome and saves so much time. And again, when we get to the point where you'll be able to train your own model, it's going to be so powerful and so quick, I think, to train or to label data sets. I really think that's the future of data annotation, right? Like we have these features like smart polygon to help doing the manual labeling. Once you do enough manual labeling, you want to have a model help you do the labeling, and then you kind of QA it. So really excited about the future. Someone asked if I can explain how smart poly works under the hood. I don't know if I could go into a ton of details on it, but it does use a computer vision model. I can tell you that much. Someone said, we saw forms. Can we track a sick goose, a different goose, or are we in a crop field? So yeah, I mean, if we had there's different ways of doing it, so it depends on your application. For example, feature points could be something that I don't know what a sick goose looks like, but if they're always more droopy or something and their neck's always down in a certain position, like potentially feature points could be something you could use to like track a sick animal. Like that's actually something you can look at too, is like how animals walk sometimes. And you can use feature points to understand someone's like walking gait or an animal's walking gait potentially. And then you could also have, if you if you have different classes of like a sick goose. So if a sick goose, or let's say we're doing like a Canada goose versus like the white goose, you could have two classes for that, like two different boxes, two object detection boxes, and you could have one as a class Canada goose and class white goose. And also, I didn't talk about this, but a lot of these labels have an option for a sub-label, where there's different ways of doing it, and it's a little complex, so I don't want to go too far into it for this workshop. But if you know what you're doing, you can train like, a multi-model process where you can classify a goose with bounding boxes and then run a model doing classification. Was that a Canada goose or a white goose or something? And you have different fields right now. I think main one you'd use in this case is going to be classification or multi-classification. And I think some more subfield sublabels are coming down the line. Someone said, can you upload a video not frames of videos and use track forward? So the track forward right now, the best way is like if you have a video file in your S3 bucket and you import that video file and break it down into frames and then use track forward. But there isn't a live video versus frames. It's always broken down into frames right now. Someone said, is this train test set already available in Google Drive? Oh, so great question. So when we get to the code part, which is right up next, I'll give you a whole label data set. I don't want to have everyone actually label hundreds of images of geese, but I really wanted to get you in the platform and try out the tools and kind of see all the different features of how you would approach labeling kind of whatever your project is after this. So don't worry, I will give you a data set in the next section, and you won't have to label 200 images of geese just for this workshop. But for your next project, you might have to. Someone said, can data annotation and data labeling be used interchangeably? Yeah, I use them interchangeably. So I might say labeling or data annotation. You might hear people say both, and essentially they're going to be the same thing. All right, so I'm going to go in. I see, again, this is awesome audience tonight. I love all these questions. I'm going to move on just because of time. It's almost 7. Believe it or not, we should totally be able to train our model in the amount of time. But I just want to make sure we get there for anyone who has to get off at like 7:30. And again, I will be hanging around though. So if there's questions I missed, I apologize. But I'm going to move on and then hang out afterwards. So feel free to ask those questions again if I did not get to them. So, and again, if you didn't sign up and you liked what you saw now, I'm going to copy that URL one more time in the chat. All right, so just before we get into the coding, just want to talk about a few popular Python libraries for computer vision. There are so many, but these are kind of the top ones that you might hear about or use like right off the bat. You have PyTorch, which is a library from Facebook. It's open source, but it's maintained by Facebook. And it's for machine learning, really popular in deep learning and computer vision. And then you have TensorFlow and Keras, and that's kind of basically the same thing as PyTorch. I think TensorFlow came first, and it's kind of their version, or it's Google's version of the very similar library. So most of the time, you're going to choose some sort of framework to work in, and it's going to be TensorFlow and Keras or PyTorch. And today it's Detectron 2, which is a wrapper around PyTorch. But usually there's one of these under the hood for your deep learning computer vision application. OpenCV is a really great library for image processing and computer vision. So when I talked about doing that green screen thing, it has a lot of really cool functions in there for like detecting colors, for detecting edges, doing all sorts of cool things like with lighting and a ton of awesome just processing stuff and some deep learning stuff as well. And they have NumPy. It is great at multi-dimensional array processing, which is actually what images become when we import them into Python. And then we have Pill and Pillow. It's an image processing library. We're going to import this today and like use it to draw out the bounding boxes. All right. So this is the link to the code book. So you're going to want to open this up. And then also at the same time, I'm going to share this link to the certification form. So this is where you can get I think it looks really cool, a certificate of completion for this workshop, if that's something you're interested in. I know not everyone is, but if you want to put on your LinkedIn or something like that, you'll be able to do that. You can fill out that Google form. It might take me a little bit to make them all for you, and then I will email them to you though. So 2 things: open this 6-skill link, which will open up this Google Colab notebook. And then the other link is if you want that certificate of completion. All right, so this is Google Colab. It's essentially Google's way of hosting what's called a Jupyter Notebook. A Jupyter Notebook's a really popular tool in data science and machine learning to allow you to write documentation and code and see the output kind of all in one place. What you will want to do is open up that link, hit save a copy in Drive. So for anyone who opens that link, hit File and then hit Save Copy in Drive. And this will allow you to have your own copy. You can now do whatever you want with it. You'll be able to change the code. You'll be able to run everything. And then also you can bookmark this one if you want, because if you really end up messing up your Google Colab notebook, you can come back to this original one, always make another copy for you. All right, so Google Colab is essentially, again, like I said, a way of hosting the notebook. You can write text. So you can double click that text cell, open up this format here, where you can write in what's called Markdown. And then to get out of this, you can hit Shift Enter. Ooh, someone said Colab work is not working. Did it not work for anyone else? Does it work for them? Let me give you the direct Colab link, not the shortened one, just in case. Hopefully that'll work for you. Said operator, no problem. Yeah, I do operator errors all the time. So one really cool thing about Google Colab is they give you access to a GPU for free. So I happen to have like a pro account where I pay a little bit of money a month and I get kind of longer runtimes on GPUs. But even just for free, you can come in, you can hit change runtime type. You don't need to do this because you copied from my notebook. It's already set to a GPU. And if you've never done deep learning before, you typically need a GPU or a TPU, some sort of accelerator that works well with training models. And GPU is the most popular one, but you can also do a Google TPU. So if you create your own notebook later and you're doing your own computer vision or deep learning stuff, you can set this to a GPU or a TPU, which is awesome. And it really breaks down that barrier of using like people getting started in deep learning, because a lot of people don't have a GPU. So you can actually do this, run a GPU in their cloud environment, which is cool. So I think that's all you need to know here. This is a code cell. Once we go ahead and run this first code cell, you can hit this play button. You can also hit Shift Enter when it's highlighted. So if you click on it, you can hit Shift Enter, or you can hit the play button. So if you don't see me hitting play, it's me hitting Shift Enter. That's usually what I do. The first time you run a code cell, it might take a little bit because what it's doing is really initializing a whole cloud instance. It's not just this notebook. It's actually like a little instance of, I believe it's running on Ubuntu, where you can actually, access all sorts of different files and stuff on it. You can also run terminal commands. So if you happen to be familiar with Linux, again, don't worry if you're not, we won't use them that much or anything, but you can use the exclamation mark and then run like a terminal command, like ls is listing all the files in a directory. So let's go ahead and run this code cell. And so one thing is that Google Colab comes pre-installed with a whole bunch of libraries. So it has like TensorFlow, PyTorch, all these libraries pre-installed. But sometimes it's kind of annoying because they always update to the latest version. And I wrote this notebook when it was on PyTorch 1.8, and I need to go through and update some stuff to get it to work on. I think the latest version is Python or PyTorch 1.9. So this is going to take a few minutes because what we're doing is installing PyTorch 1.8.1, which is what I wrote this on. And now by default, 1.9 is installed. So just be careful. If you ever write something in a Google Colab notebook and you want to come back to it later and something's just not working, it could be that the dependency changed so that now there's like a new version of something installed. Someone asked if it's part of GCP. I mean, I don't know technically where the line of GCP ends in Google, but to me, it feels like it is. But I mean, it's not really. You don't have to sign up for a Google Cloud account or anything like that. But I'm sure it's using their Google Cloud stuff behind the scenes. I don't know if that's a good answer to your question, but that's probably the best I can answer it is. I'm assuming they're using their own product, for everything behind the scenes, unless it's completely separate. But you don't have to have a separate Google Cloud account or anything like you normally do for GCP. You can just have your own personal Google account. And this can actually mount to your Google Drive, which we'll see in a little bit, because that's the way I do recommend storing your own data sets and stuff in the future. So don't worry. You might see these errors. I think it should be fine. Yeah, so like in this case, it's saying like, hey, there's a version of Torch text, which is something for doing stuff with text in PyTorch. We're not going to do that today. It just says it requires 1.9. So don't worry about these errors. They should be fine as long as you run every code cell in order. So we can run this next one. We're just going to install PyYAML and PyCoco tools, some other dependencies for Detectron 2 and the work we're going to do. And then these were checks in there because I was having problems in the past with them updating the dependencies, right? So you can do stuff like torch_version and see exactly which one is in there. And then we're going to install Detectron 2. So you can see this specific URL is even looking for PyTorch 1.8. And so you'd have to update this and maybe a few other things to get it to work with the 1.9. So that's just where the top part is just uninstalling a library and reinstalling one. And this will take a minute. Shouldn't take too long. A lot of requirements are already in Colab. Looks like it's done. Again, don't worry about kind of this warning or anything. I think everything should be fine. We're going to install a version of Pillow, which again is the visualizing library. And again, don't worry about the restart. It should be good. We should just run everything in order and be good to go. And then here we're importing some dependencies into our project. So this, I might have said importing up here, but this is really downloading it into our instance. And then if you've never done Python before, usually import libraries into your project using this import statement. And then like we installed Detectron 2, so we're just importing that in. There's some various specific things from Detectron 2, as well as a couple other libraries like NumPy. CV2 is OpenCV, and this specific function for CV2 imshow. CV2 has a function for kind of like writing out an image and showing it, but the default one actually like always breaks when you do it in Google Colab or Jupyter Notebook. So they have this specific one that allows it to work in here. All right, and then we talked about already labeling our data set, but I have this little section in there. So again, if you need to sign up or whatever, or join the Slack channel or read the documentation, you can go do that here. And then I did link this before. This is a link again to where really this data set came from. Was originally made it for that project of doing kind of the synthetic data and wildlife model there. But we're going to load in the data set using Git. So I have this data set of, I forget the exact numbers, something like 200, 300 images of geese labeled already. And this is on GitHub. So you can also just visit this URL if you want to go get that data set and look at it. But we're just going to git clone it, which is bringing it down into our project here so we can access it. And then I am going to list directory ls just into that folder and see that there's a folder of images and there's 3 JSON files. We have that train, test, and validation JSON file, and we'll get to that in a second. And then if I look in that image folder, you can actually see that there is a whole bunch of images. And these are all the ones that I labeled. So now we have our data set in our project. I just want to mention real quick. So I have it stored on GitHub, and there's a couple ways of bringing your own data set in. So after this workshop, if you want to go work on your own data set and bring it in and build a model, there's a couple ways of doing it. And I'm going to show you them right now. So you can click this little tab here, or directly on this folder one, I guess, actually. Mine might look a little bit different because I created this folder and it automatically mounted to my Google Drive because I've done it before. But what you can do is you could hit this connect to Google Drive or mount to Google Drive button, and it'll ask you to go to this other URL and like get a code and paste it in. You don't need to do it for this workshop, and it's not that hard to do once you do it once. And once you do it in a notebook, it doesn't really ask you again for it. It's just essentially you're verifying, hey, I'm okay with this notebook, connecting to my Google Drive. And once it's connected to your Google Drive, you can drill down into all of your folders and go get your data sets in there. And so I'd recommend doing that because it'll always, like, you won't have to download it every time, and it'll always live there. And then once you're connected to Google Drive, you can just like rerun your code cells. And I'll show you how to put it specifically in right here where we actually import our data set. Another way of uploading it is you could go get all your files. So like these are the ones that we exported. You could highlight them all. I'm not actually going to do it because I don't want to wait for them to upload. But then I could just drag all of them, including the images, into this little section here. And they'll upload into your little instance, your Google Colab Ubuntu instance. But the problem with that is once you kind of close this out or you get disconnected from your runtime, that's going to go away. So really the best way and the most persistent way is to connect to your Google Drive and create a folder for datasets, and then you'll just replace these URLs to wherever your data set lives. And we'll look at that in a second. So let's go ahead and import our data now. So we are using this register Cocoa instances. That's that function I talked about that actually knows how to read in all that Cocoa data. And it makes it way easier because we don't have to write a function to look at that crazy JSON mess and then parse through it. So go ahead and run this code cell. And what's happening is we're running that function. We're naming our 3 data sets. So we have a train, validation, and test one. And then we have the path to the JSON files, and then the path to where the images are. And so if I was going to replace my data set here with one on my Google Drive, I could come in. I think I have a toy data set in here. I could come in, I could get this train JSON folder. I could just hit copy path, and then I would just replace this. So if you were doing this with your own data set later, you want to update this kind of path to wherever your train.json file is. And then you want to also tell it where the images are. And this is one part that can be a tiny bit confusing. If we look at our JSON file, the path to the image will always reference that image folder, the IMG folder. So because when we generate the data set, we put everything in that IMG folder and we know where it lives. So it's common for me to want to be like, cool, I'm going to copy the path to my image folder. But that IMG part of the path is already in our train.json. So we really just want to have it like this. Like we want to have the folder above that IMG one. So it's going to read this JSON folder in, and then it's going to look at this path and look for that, that image folder. And if that sounded a little confusing, don't worry. Once you do it like once, it really isn't that hard. And it gets really easy to just make a data set folder in your drive, upload there, and then copy those couple URLs, and you're good to go. So you just want to do that for the train JSON, the validation one, and the test one in this case, because we're building those 3 data sets. So now we ran this code cell, we registered our data set. It's always really important once you read your data set in to kind of verify that it read in how you think it should have. So in this case, we're using their pre-built function. I probably trusted in this case that it read in correctly. But maybe we use something to generate our annotations and something was off there. Or I've been in this situation before where I built my own custom like data loaders, and I read in my data, and I made a dumb mistake somewhere in my code where I read them in like reverse or something. So my rectangle was like down here, not actually on the object. So it's always a really good idea to just do like a random sample test of your images and make sure they read in like you thought they should. So that's what we're doing here. It's just outputting 3 random images from our training data set. And you can say, yep, it looks good. This bounding box is around the goose. And I feel pretty confident with it. You can also look at this kind of data set dictionary. This is actually what it looks like once we parse it with that Cocoa function. So again, don't worry if this looks crazy, but really this is just our coordinates for those bounding boxes. So when we train our model, it knows to look in that area and try to extract features that we're looking for. Any questions on that? Is everyone feeling good? We're going to get to the training right now, and you'll train your own computer vision model, which will be hopefully super exciting. All right, so go ahead and run this code cell. And I'm actually going to go ahead and run this code cell under because it takes a little bit to train the model. And I'll come back and talk about this code. So go ahead and hit run, and we'll just make sure that it's running before we go back. And then I'm going to talk through all of this. But because this is one of the most time-consuming parts is training our model, but you'll actually see it won't be super long. All right, we're getting some output, and it looks like it's training. All right. Let me scroll back up. So here, I'm not going to go too deep into this part of the code. You can go read this Medium article if you want. I'll share the link here. And this will talk about kind of why this class is made. But essentially, one thing I don't like about Detectron2 is there isn't a super easy way built in to do the validation while training. And that's where a validation dataset comes in. So when we are training our model, we can look at some metrics we'll see in a second, and we can see things like the accuracy is going up or our loss is going down, which is typically something you want in most deep learning models. But that's almost always going to happen with your training data set, and if it's training correctly on it. So what you really want to do is while your model is training, after a certain amount of iterations, so like it's going to look at our images, 300 times or something like that. Well, we would say after 50 iterations, see how well this model performs on a data set it's never seen before. So look at images that aren't part of the training data set and see how well it generalizes on those images. And that's where the validation comes in. And then the test we can do once we feel confident that our model is trained. So the validation is really to give you more feedback while you're training your model and adjust things like hyperparameters, which we'll look at in just a second. So it's kind of like a data set for you as the human in the loop during training, which is cool. Someone said they got an error on cell 16. Make sure, I'm not sure which one was cell 16. Oh, this one. Make sure that you ran all the code cells beforehand. Pretty much anytime someone gets that error, it's because they missed somewhere. And as a little tip, if you really want to, you can go to runtime and hit run all, and that'll run all the code cells at once. So now our model's training, we can go, oh, sorry, let me talk about this real quick. So this is how we configure our training, configure our model for training in Detectron2. We have this kind of config, get config a situation happening here. We're creating a variable called config. And then we're saying merge from file model zoo. This is the model we want to train. So you can go to this model zoo link up here and kind of see all the ones built into Detectron2 that we could use. Typically, you might want to use just this faster mask RCN for COCO detection, or maybe you would want to copy this and replace it, and this would be used for instance segmentation. So the COCO detection is for object detection, instance segmentation is for instance segmentation. And so in this case, we're saying we want a faster RCNN model, and then we have this model.weights, and we're saying get this checkpoint. The checkpoint is the pre-trained weights. Like I had mentioned during the transfer learning slide, that most frameworks come with these pre-trained weights, and that's what we're doing here. We're saying we're not starting from zero. We want to take all of your pre-trained weights, load them in, and then we're going to fine-tune it for our data set. This is an important parameter to change because you'll want to change this depending on how many classes are in your data set. So for this example, we're only training on Goose, right? So the example is 1. If we're doing Goose and duck or the different types of geese, like if we had 2 of them, we would change this to 2. Then we're passing in our trained data set. And just as a tip, if you're missing this comma, it'll really throw an error, and it might be hard to find out what's going on because it's expecting it to be a tuple, which is a data type in Python, and adding that comma creates a tuple here. And you can pass in multiple data sets. That's why it's a tuple. So you can have multiple data sets that it's training on. This max iteration is how many times we're going to look at our data set. So in this case, like I had mentioned, it's going to look at our images essentially 300 times and learn patterns from it. depending on your data set, if it's much more complex data and there's a lot more variations, you might want to add a lot more iterations to it. So if 300 in this case, it won't take us too long to run. And you'll see that we'll get pretty good results for detecting geese in a park. But if you were doing, like people in a whole bunch of different settings, you might want to up this max iteration more. So you could try it and see how well it performs, and then try it with more and see how well it performs. And then we have a couple other ones I won't go really deep into. They're a little bit more advanced, but we have something called a learning rate that really kind of is how your model learns from the data. And then we have advanced things like number of workers if you're doing distributed training across multiple GPUs, how many images per batch you're reading in, kind of some other parameters that I won't really get into here. And then we're creating our output folder, which is where the model is going to save at. And then this is where we run our validation data set. So again, while our model's training, we want to see how well is it really doing on data that is likely we're going to see in the real world, but it's not part of the training data set. And this area is where we specify every 50 iterations. We want to take a look at that data set and see how well it's running. And then this is just calling it to do the training. And then let's look at the output. We have a whole bunch of stuff here. This is actually that ResNet backbone I had talked about before. So if you've seen deep learning models, this might look familiar. And if I scroll down, there's a lot of stuff going on. It'll tell you that, hey, we're reading in 110 images of geese, but inside of those 110 images, there's actually 260 instances because most of those images have more than one goose in them. And you get some other kind of feedback. Don't worry about this. It says like, hey, skipping this thing, but that's because essentially we took those transfer learning weights, but then we are saying now we only want to look at a goose. So it's just saying like something doesn't quite fit here, but that's what we're doing. And then this is our validation data set. So we have 37 instances that we'll look at during training. And there's a whole bunch of stuff you can kind of read in here. Really, the important stuff is coming up. So this is the validation data set output. So when we first started our training model and we looked at our data set 50 times, we get the score back on our validation data set. And AP stands for average precision or mean average precision. It's a common way of measuring things like object detection and instant segmentation. I actually have a link later in this notebook that you can go read more about this metric because it is important to kind of understand. But at a high level, it's really measuring. So if you're doing classification, it's easy, right? Because if you're saying, is this a dog or a cat, and it mispredicted, you could just say, hey, you're wrong. But when you're doing something like object detection or instant segmentation, usually it's doing some sort of prediction, but you really want to see how, you really want to understand how much it's off. So for example, right, if we were doing object detection on a cup and the rectangle was off, but it was still kind of on the cup, that's where the mean average precision really comes in. And it's more adjusting about like, it's how to adjust to the bounding boxes to the correct place. Because it's much more complicated than just saying yes or no, you were right. It's how much were you off and how can we get to a better place. And you can see that here's kind of our total loss. Again, if you're familiar with deep learning, loss is very common to look at while you're training. If you're not, don't worry too much about it. It's just a metric to look at while training. Usually you want it going down and you want accuracy going up. And we kind of see this. So the next time, then after the next 50 iterations, our accuracy or AP went up to 72. The higher the number here, the better. So we want our average precision to go up. And then after, what was that, 3 or 4 times, essentially we end up with 82 in this case. And there's, again, the article explained kind of these different variations of it, like how accurate do you need this to be and how much can it be off? But essentially the higher the numbers here, the better. And yeah, so we can see that kept going up. And then if we run this next cell, this is called a tensor board. And this kind of visualizes what happened during training. Some people during the workshop said this doesn't load for them, but don't worry if it doesn't load, it doesn't ruin anything. I don't know if some people might have an error with this. Someone said, please put the recording up. I will put the recording up. And hopefully it'll be up. I'll try to get up tomorrow. But if it isn't tomorrow, it'll probably be Monday. So here we can see we can actually see our average precision kept going up. It actually kind of went down at the end there. That could be like, where we need more data, we're overfitting on our model or something. Like if we kept running it for a whole bunch more iterations and the AP kept going down, then maybe we would want to scale back our training iteration. So because you can overfit on your data where it only learns like how to recognize the things in that training data set. And that's why it's important to have this separate validation data set, because you can start detecting things like, ooh, my accuracy is going down, but it wasn't going down on the training data set. It's going down on data it's never seen before. All right, so I'm going to run through the rest of the stuff, I think, fairly fast, but I will come back and go through anything that we need to. If anyone has any questions, I just want to make sure everyone, I see some people saying, it's kind of late for them. So I want to make sure that people who want to kind of finish this can get to it. So here, now we're kind of setting up our model again, kind of like we were for training, except for we're going to set it up so that we can use our weights that we just trained. And we can read in an image or video and run the model on it. So here we're saying config, kind of like we saw before. Then we're saying merge from file, model zoo, just like we did before. This needs to be the same model you chose to train with. So if we change this out to the segmentation model up above, you also need to change that out here. Otherwise, it'll throw an error, I think, when you read in your data set. That will definitely not work, that's for sure. And then just like before, we have that model.weight, but instead of doing the COCO model zoo like we did before for transfer learning, we're actually passing in our weights. So we have this output folder here, and we can see this is our model final path. If you had, for whatever reason, upload a model or something, you want to change it out, again, you can navigate in here, hit copy path, and then paste it in here. And then we're reading in our test data set. That's so we can do some final test metrics. This needs to be, again, the same number of classes that you trained on. So again, it's just one for geese or one for goose, but if it was goose and duck, it would be 2. And then this is kind of important. So this is the ROI threshold. Our ROI in this case stands for region of interest. And here we're saying only draw the prediction out if you're 90% confident that this is the object we were looking for. So in your case, if you come back to this and bring in your own data set, and it's a much more complex data, much more complex object, and maybe it's not as confident that it's that object, you might want to scale this down. So you could go to like 60 or 70 just to make sure that your model's working. And then you want to get to the point where you feel pretty confident, like it's always going to draw out when I want it to. In this case, it's going to work pretty well on the goose, and there isn't a ton of variation between all the different geese. So the 90 is going to work well here, but you might want to scale this down to like 80, depending on your use case. So let's go ahead and read in this image. So this is from our test data set. And you can see we're reading it in. We have this path, and then we're reading in with OpenCV. And then we're getting our outputs, and we'll actually look at this in a second, because actually the important thing is getting this kind of output data, and then it's what you do with it that's important. And then we're using the visualizer from Detectron2, and then we're outputting those predictions and drawing them out. So as humans, we visually see kind of what's happening. So you can see it says 0, that's a class 0. Python, like most programming languages, start indexing at 0. So 0 is like the first class in the index. And then we're 98% confident that it's a goose. So did anyone get to do this yet? Also, I forgot to mention, sometimes it'll take you a little bit longer to train your model than me or for any other people, because you get kind of randomly selected based on what's available in your instance of like what GPU you get. And that really affects the training time. So if you got a less powerful GPU, it's possible you could still be training, but I'm still going to go through just because of how late it is, and you'll be able to catch up and just keep running all the code cells. So someone said cell 16 is taking 10 minutes to execute. I forget which one is 16. The training can take a while if you get a lower end GPU. I think this is cell 16, right? Or am I wrong? This should execute pretty much immediately. If you get an error, if you're still training, just keep waiting, because it can take a little bit. But if you get an error and you can't fix it, go to runtime, hit factory reset runtime, and then you can just hit run all, and that'll run all the cells sequentially, and everything should work. But it can take a while to train your model. All right, so was anyone able to run detection on an image yet, though? Someone probably had a pretty good GPU. All right, someone said yes, awesome, congratulations. Everyone who got it, awesome. Especially if you've never done computer vision before, or if you've never done machine learning before, congratulations, because this is like a really, really cool model that you've now trained, and you know all the steps of how to get here. So you know how to label your data set, and then you know how to train a model, kind of bring that data in, train a model, and then run it, in this case on images. Next, we're going to run it on a video, which is really cool because it's awesome to see it on an image. I think it's even cooler to write these like outputs to videos, and it's really cool to share. So if you're trying to show off what you can do, videos with visualizations are really cool. And if you're looking for a career in computer vision or something, share it on LinkedIn. And also, if you do make your own model and you create a cool video, again, we'll get to the video part in a second. Feel free to tag me in it too if you share it on LinkedIn or Twitter. I always love seeing what people build. It's always really cool. All right, so let's real quick look at what the image looks like when we read it in. So without writing it out with this like imshow function, the image is just this giant set of arrays, and that's really how an image is read in Python. It's an array, a multi-dimensional array, and there's 3 values in here. Those are actually red, green, blue values. All the channels, right, for making up the pixel colors. And then let's go ahead and look at what those outputs actually look like. So we drew it on an image above, but sometimes you don't actually need to output the visualization. It's really cool to do so because it looks awesome to us humans. But sometimes when you're making a decision of like what happens next after this, you really just need this that's in here. So if we look at those outputs, you'll actually see there's our coordinates to draw the rectangle. And you could use this to see if they're overlapping with other rectangles. You can also see the confidence score, and you can also see the predicted classes. Again, it's 0 for Goose in this case, and also the number of instances. So just with this data, if our application was to count how many people are in a room and send an alert if there were too many of them, we could actually just do that in here and be like, well, the number of instances is 2 or 10 or whatever it is, like, text someone or send an email. So a lot of times you won't actually need to write out the visualizations, but they are really cool to look at. And they can be really good for troubleshooting as well. So you do often want to see the visualizations, but if you're doing kind of a next step in some other part of an algorithm, like in a layer afterwards, you really just often will want this data here. Just to mention too, so you'll see this like 2 device or 2 CPU or 2 GPU a lot in PyTorch. And remember, Detectron 2 is kind of a wrapper around PyTorch. That's us like moving those predictions we made on the GPU off and onto the CPU. So we can just like write them out like normal here. So let's do, here's a quick little application. Again, it just says how many geese were detected. That might be what you need if you're just detecting how many things are in frames. Do one more image here. You can see it's detecting geese. Awesome. And let's go ahead and I'm just going to run quickly through these last parts, and just so we can start running it on the video and downloading the video, which can take a little bit of time or a few minutes, not too long. But here, this code cell is just running those evaluation metrics, kind of like we did before on our validation data set, but now we're looking at our test data set. So it's pretty common while you're training, you run it on a validation data set. Once you feel pretty confident that your model is in a good place, then you use a separate holdout test data set that you never even use to even adjust anything in your model and see how well it did on there. So again, this is just going to put out like that mean average precision score here. And this link, again, you have these links if you're in the notebook, so I don't really need to share them in here, but this link here talks way more about kind of these metrics. So I totally recommend if you're like, hey, I want to dive deeper into what the average precision actually is doing, then go read this article here. All right, so let's run detection on a video. This is actually just shows this video here. So it's just a video I uploaded of geese walking around, but this data wasn't used in the training data set at all. So it's kind of a whole new data. We're going to pip install a library called YouTube download or YouTube DL. That's going to allow us to download my video here. Going to run this cell, and it's going to download that video at 22 frames per second. And the output is going to be video.mp4. And then we don't need to run this for this workshop, but I just want to mention that you can use like a library called ffmpeg to cut that video down. So our video in this case is only like 8 seconds long. It won't take that long to write out. But sometimes you might have a video that's like, minutes long or an hour long, and you just want to make sure your model's working before you spend all the time writing it out to a video. And so I recommend doing something like a 6-second clip and verifying it looks like how you want it to look like before you spend all the time running it on like a several minute long video. And then I'm going to run this code cell. I'll come back to what's happening, but this is the one that can take a little bit. And I'm going to run the one afterwards. So you'll see this is starting to go. It has a percentage sign, and then this is going to download the file when it's done. So what's happening here is we're extracting some information from our video file. We're pointing to that video.mp4, which is the one we downloaded here. If you wanted to make the clip, if we did make this video clip, again, you would just navigate to where it is in this menu and then copy the kind of the URL or path to it here. We're getting information like width, height. So we're going to use this to build our video. We're going to read in these frames, and then we're going to write them at the same resolution, pretty much the same resolution as the video we're reading in. And we're using a video writer function of OpenCV, and we're going to save our video to out.mp4. There's some other kind of settings you can do in here. Then we're creating a variable v, which is going to be our video visualizer from Detectron2, which allows us to write out the video kind of pretty easily. We're going to pass in our test data set, and it's really so it can read some metadata from it. So in this case, the metadata would really be the class. So it'll actually write out Goose on it versus 0. And then we have this function here. And all this is really doing is just using a while loop to say, while there's still frames in the video, take the next frame and run the model on it just like we did up here. And then pass that new, so take the frame, run the model, write those visualizations out just like we did before, and then pass the frame with those visualizations drawn on it out of the loop. So then we can use the video writer function to create a video. So here, this is done running for me, and it can take a few minutes to download here. It actually usually isn't that long, but I've noticed while doing the workshops, it takes longer, and maybe that's because I'm streaming or something like that. We're almost there. Did anyone get a download their video yet? Someone said yes. Awesome. Hooray. Congratulations. Someone said still crunching. Yeah. Sorry if your training is taking a long time. That's just you got a lower end GPU, and unfortunately there's nothing I can do about it unless you sign up for the Colab Pro or whatever. You're more likely to get a better one. Is there a reason why I did a while true instead of for loop? Like, I guess I could do a for range or for range of frames, I guess, right? Like I could take the number of frames from here and do a for loop. I don't think there's any other reason besides that's just the way I did it. Like, I don't think there's something more efficient about it or anything. I'm sure I could make this better, to be honest. Mine's almost done. Someone said 1 minute before they're done. Is that 1 minute before you're done training? Or yeah, sorry if you got a slower training cycle, but hopefully, you'll be able to run all the code cells after that and catch up and get your output. So let's open up this output, and hopefully it worked, and it did. We have detections running on these geese. Woo! And so if you are running a little bit behind, this is going to be the result you get. And again, you can follow all these steps now, bringing in your own data set. And again, you can do the instant segmentation just by swapping out that one URL. Instead of doing the Cocoa detection, do the Cocoa segmentation from the model zoo. And then there's a lot of other resources in here. One, again, if you are interested in the certification, there's the form for that. And then also there's other sources here. And I'm going to share these links in the chat. And then I'm going to stop recording, but I'll be hanging out if anyone has any other questions. But that's kind of it in a nutshell. We went through, we saw computer vision applications. Hopefully some of them were cool and maybe new to you or sparked really cool ideas. Then we learned how to label our data set and kind of do that faster with some cool AI powered features, and then export data set and then import our data set into Google Colab and use Detectron 2 to train a detection model. And I can't wait to see what you all build. And again, I'm just going to stop the recording right now and I'll be hanging out for a little bit.